We'll now evaluate for the problem we have been looking at, which is a nonlinear least squares problem, the Cramér lower bound. Because it is a nonlinear problem, we cannot use the results from the least squares to obtain the covariance matrix of the estimated parameter x. So we will resort to the CRLB. So we will quantify the accuracy obtained with an unbiased estimator. We hope that our estimator is close to being unbiased. So the CRLB for an unbiased estimator says that the covariance of the estimation error, covariance of the estimate, that's the same thing, is greater or equal to the inverse of the Fisher information matrix denoted by J, which is given by the expected value of the gradient of the log likelihood function times its transpose, evaluated at the true value. And this is del x little lambda of x times its transpose. Now, for this problem we have been looking at, the angle-only localization problem, the Fisher information matrix can be shown to be by taking the gradient on the Gaussian density. You end up, the quadratic becomes a linear function from the exponent, multiplied with itself, again becomes a quadratic, and you have outside it the gradient of the function h. This is an exercise that's highly recommended to go through to connect this expression and derive its final form. So what we have here is the sum of dyads, as you can see, the matrix J, which is 2 by 2 because this is a two-dimensional parameter we are estimating. There will be 3 dyads that are summed up. The result is divided by the scalar, which is the variance of the noise. Obviously, the larger the noise, the less information we have, so that's just a factor of proportionality. So next thing we are going to do is use for that passive localization problem the iterated least squares and the maximum likelihood estimator on 2 different scenarios. And the quality of the scenarios, whether you have a good sensor to target geometry or poor sensor to target geometry, will be measured by the Cramér lower bound values. And these are illustrated as follows. If these 3 points from which the angle measurements are made are far apart, as a matter of fact, if they are at 2 of them are close to being orthogonal in terms of the line of sight, then that is called a good geometry. If these points are close by and the lines of sight are at small angles from each other, we have what is called poor observability. And this can be seen easily by if you perturb the angle on this and on this, their intersection can be moving in this direction, can move up or down significantly because you have an erroneous angle measurement. So this is more sensitive. Now the exact quantification can be obtained by evaluating the CRLB. Okay, so what we have would be a number of Monte Carlo runs with the corresponding CRLB values where the measurement standard deviation is 1 degree. Now both techniques, the numerical search techniques, the ILS and the ML iterations, terminate when the norm of the difference between 2 consecutive estimates is less than half a meter, or if we made more than 50 iterations. Typically, both algorithms converge in about 5 iterations. The initialization is done by the intersection, a simple triangulation of the first and the third line of sight measurements. As we see, the results are pretty much the same for both techniques. We have a good observability and the poor observability. We'll see this quantified in a moment. Here is the first scenario where you can see that the sigma CRLB for the x-coordinate is 245. The sample standard deviation based on 350 observations is very close to it. And very similarly for the eta or the y-coordinate, we get about the same result. Now, remember these numbers, 250 and about 500 here. And now we go to the pool geometry. It's exactly the same accuracy of the measurements, but the three sensors or the three locations from which the angles were measured are closer to each other. Now the x is about double from 250 is 465 or so, and the eta coordinate from 500 is 2700 almost. So really, by making angular measurements, you have a reasonably good way of figuring out the lateral error, that's x, but not the distance, the location. So the range from the sensors has a fairly large error in this case. So what we have now is the two gave the same results, but one difference is the iterated least squares outperforms the maximum likelihood estimator in the numerical search. And the problem with the Newton-Raphson, which relies on the Hessian, which is a second derivative, because you have inaccurate estimates, the Hessian is not very good, so you end up with a slower search and might not hit the maximum. Now, there is an important concept, and this is related to localization, and it is used also extensively in the global positioning system, and it's called the geometric dilution of precision. This is defined as the degradation of the overall position estimate, root mean square error, versus, in this case, the cross-range accuracy of the error, of the sensor. This measure angle at a certain distance. If you multiply it with the sigma, the standard deviation of the angle measurement error, which has to be in radians. Radians is a dimensionless quantity, multiplied by distance gives you distance. So you have this, the cross range error, the error perpendicular to the range vector in the denominator, and this is the overall position error, root mean square value. So again, this ratio is a dimensionless ratio, and it tells you what is the dilution of precision between the single measurement, which is in one direction, and the combined overall error in position. And this is indeed very sensitive to the geometry. For the good situation, the good geometry, the G drop was between 1 and 1.3. For the poor geometry, it was around 4. So this 4 indicates a degradation in the overall position error compared to the single position measurement error. The next topic we are going to consider now is polynomial fitting of a number of data points. And these will be noisy data points or noisy measurements. Assume now that we measure in the presence of additive noise the position of an object moving in one dimension with constant velocity. The motion is given by initial position x0 and velocity x0 dot. So the position at time ti is x0 plus x0 dot ti. But what we observe is that quantity, the zi, in the presence of additive measurement noise. So the motion is characterized by the unknown parameter, two quantities here, x0 and x0 dot, initial position and initial velocity at some reference time that we denote the t0 as 0 for convenience in this case. In statistics, this is known as a first-order regression, and we can write it in a compact form that will lead us to a least squares solution, that zi is h of I x plus wi, where the h of I is 1 and ti, so this is a two-dimensional vector. So what we are really doing is we are trying to estimate the parameter x, or to do a polynomial fitting, and in this case this is a first-order polynomial, a straight line, to a set of noisy measurements. Now, if the noises wi are independent, identically distributed, zero mean, and with variances sigma square, then the covariance matrix of the stacked measurement noise vector is R super k equal to I sigma square, where I is a k by k identity matrix. So we are setting up now again the least squares solution. It's going to be different slightly than what we had before. The R is an identity times sigma square, but the H is a 1 and t for the corresponding time. And because this is an identity matrix here, an identity matrix here, it really boils down to an hk prime, hk inverse, hk prime, z super k. So this is a stacked vector of the measurements, and hk is the stacked matrix of the 1t single measurement matrices. We can also simplify the parameter estimate covariance, which is hk prime rk inverse hk, the whole thing inverse, by noticing that with an I sigma square here, you don't need the I, and you can pull out the sigma square. Remember, sigma square to minus 1, another minus 1 ends up as a sigma square here. Now, the recursive solution for this problem, this is a purely linear problem, and the batch solution can be rewritten as a simple recursion, algebraically 100% equivalent to it. New estimate is previous estimate plus gain times new measurement minus predicted value of my current measurement based on the previous estimate. So this is, in the expression in the square brackets, is the residual, this is the gain, and this is the product between the gain and the residual is the correction term. As indicated, whenever you have a recursion, you have to initialize. Now what we have is a two-dimensional parameter vector, which would have to be initialized from a minimum of two observations, because otherwise you cannot solve. With one observation, you cannot solve for two unknowns. So for k equal 2, we can write the batch solution, and we have first the covariance matrix of the estimate, that's estimation accuracy, for the two parameters based on two data points, two measurements. Then we have the batch estimate from two measurements of the two parameter vector, and as you can see, if we solve it, this is for the position, this is for the initial velocity. Clearly the initial velocity is the second minus the third divided by the time difference, and the initial position is just a linear combination, weighted combination of the two measurements. So all this follows by substituting here P2, the specific form of H2 transpose. There's a transposition here, so there's the first one, this is the second one, and here's the stacked vector of the two measurements. Now, the covariance matrix that we have can be written explicitly, it turns out, in terms of the TIs, these are the times at which the measurements are obtained, we can denote compactly with S sub j the sum of Ti to the power j for j0, 1 and 2. Obviously for j0 this is just k plus 1 because each is a unity. This is sum of the times and sum of the squares of the values of the times. And the pk plus 1 has a nice simple closed form expression in terms of these three sums. And a similar simple version of the gain for our estimation update, because this is what we are doing. We do an update. The new estimate is equal to the previous estimate plus the correction term, and this whole operation, this process of changing from the previous estimate to the new estimate, is also designated as the update of the estimate. So this is a pH prime R inverse. This is the gain. Again, has an explicit expression in terms of the sums as well as the time of the last observation. Now, up to this point, everything was done with arbitrary sampling times. In most cases, the sampling points will be uniformly spaced. Therefore, we can simplify by finding explicit expressions for these sums. So, if the samples are uniformly spaced with interval or period t, Ti is it, I going to up to k plus 1 here. The sum S0 is just k plus 1, that doesn't matter, but the sums S1 and S2 can be obtained explicitly as based on the sum of I and I square, I1 to k plus 1 really. And we have now explicit expressions of the gain for the k plus first measurement, or at time k plus 1. And you can see here that the position gain goes down roughly as 1 over k. The velocity component of the parameter will have a gain going down approximately as 1 over k square. And we have the explicit expression of the covariance from k plus 1 observations. Again, for the position, the variance goes down as 1 over k. For velocity, it goes down as 1 over k cubed. And there's a cross term because there's a covariance. The position and velocity estimates are correlated. So, as the covariance goes to 0, the gain also will go to 0. Obviously, if I have a perfect estimate or nearly perfect estimate of variance 0 or nearly 0, I don't need new information. There is no need to update the estimate when the covariance is 0. So this is why, as the covariance goes to 0, at the same time, the gain will also go to 0. And we'll discuss this because in the real world, this is not going to hold that we get perfect information. So in the case of dynamic systems, we don't want to run an estimator that the gain has gone to 0, because in practical situations it is an illusion that you have perfect estimates. Now, before going on to dynamic system, we have a few more static problems that we can handle. Namely, not just the fitting of a first order polynomial, the fitting of a straight line, but the fitting of an arbitrary order polynomial. Assume that the evolution of the position of an object is modeled as a polynomial in time of order n. The reason we write the true position psi of t, sum aj t to the j over j factorial, we prefer a j factorial here because there is a clear meaning. A0 is position at the reference time, A1 is velocity at the reference time, A2 will be acceleration at the reference time. So when you start taking derivatives, there's always a j coming out, and that will cancel with the denominator, and therefore we have a physical meaning for these aj's. And what we'll do is use the least squares. This is a linear problem again, because we make direct observations on the unknown parameters a in the presence of some noise, and these are the gains on those parameters, the coefficients, known coefficients multiplying those parameters. We also assume that the times at which the observations are made are perfectly known. Again, in the real world, there can be errors in those times for various reasons. So we'll now solve the problem of polynomial fitting, an nth order polynomial fitting. And we can go back to the first order polynomial, which is constant velocity motion or a straight line fit, and we have these expressions for the case that the samples are uniformly distributed, and now the reference time t equals 0 is the center of the batch. So what we have now is a reference time, and that's where these coefficients are the derivatives. And for convenience of these expressions, we have a batch, and the reference is in the middle of the batch. The very first solution was at the beginning of the batch t0. A second order polynomial would be a constant acceleration motion or parabolic fit. Again, we have expressions that become a little bit more complicated, and now the a0 hat, a1 hat, and a2 hat are the position, velocity, and acceleration estimates, again at the reference time t equals 0, which now has been selected at the center of the batch. Third order polynomial is a cubic fit, also called constant jerk motion, because jerk is the derivative of the acceleration. So it is, we have four parameters: position, velocity, acceleration, and jerk. That's why it's a 4 by 4 matrix, and we have explicit expressions of the times based on these sampling times of the estimates of position, velocity, acceleration, and jerk. And again, these are symmetrically distributed, so Ti is K, is an IT in this case, with the reference taken in the middle, however. Okay, one interesting thing, if we look at the expressions of the covariance matrices, when we increase the order of the polynomial fit, namely we are fitting a higher order polynomial which has more coefficients, the variances of the parameters will increase. Obviously, you fit a straight line, that's 2 parameters, you fit a cubic, that's 3 parameters. Remember, you have the same amount of information in the data, something has to give. You have less information per parameter when you fit a higher order polynomial. For the choice of the reference time, as we have done here, the parameter estimates will be position and its derivative at the center of the batch. These increases take place for every other parameter. Namely, if we fit n equal to 3 will be a parabola, n equal to 2 will be a straight line, there's 2 parameters. You can see that for the position we get the same. P11 is the position component. For the velocity component, if you fit a parabola, you already have a variance larger than if you fit a straight line. So this is the order of the fit, and this is based on k samples, and this is for the position, and this is for the velocity. Now, an additional point of interest is, having set the reference time at the center of the batch, we might be interested in obtaining from our fit an estimate of the position at another time. We have the position in the center, that's the A0. What if we want the position at the edge, the fitted position based on the parabola at the edge of the data set, or even outside the data set, like predicting the next position? We'll illustrate this mapping of the estimates to an arbitrary time by assuming a constant acceleration motion that's a three-dimensional vector. We have a second-order polynomial with three coefficients. Position, velocity, and acceleration are estimated at the reference time, which is the center of the batch. Based on these estimates for the center of the batch, the estimate of the corresponding position, velocity, acceleration vector at an arbitrary time within the batch, arbitrary point or outside the batch, that will be the prediction or extrapolation based on those k measurements, uniformly spaced, and the x hat at an arbitrary time k, arbitrary time t, based on the k measurements we made, will be given by the estimated vector based on k measurements at the center of the batch, as a hat k, pre-multiplied by a matrix phi, and this phi, the first column has 1 t squared over 2. You can clearly see that the position at any future time is the predicted position, or extrapolated position is the position at the center of the batch times the estimated velocity at the center of the batch multiplied by t times the acceleration at the center of the batch multiplied by t squared over 2. For the velocity at an arbitrary point in time is the estimated velocity at the center of the batch plus t multiplying the estimate of the acceleration at the center of the batch. And because this is a constant acceleration model that we are using, the acceleration at any time is the same as the acceleration at the center of the batch. And we have to remember, this is a model. And one of the main issues in engineering analysis is what model should be used. It's not only how we solve the problem for a model, but which is the most adequate model that we should use. And we'll answer this question soon. Now, once we do this extrapolation based on the parameter estimate for the center of the batch, again, position, velocity, acceleration, we will also have a covariance associated with the estimated or extrapolated value at time t based on those k observations that take the pk, this is the covariance of the parameter estimate at the center of the batch, pre and post multiplied with the phi t and phi t transpose. You can come up very easily based on this with similar transformation for lower or higher dimensional parameter vectors. We'll take one example and we'll consider a two-dimensional case, which is a straight line fitting, in other words, a constant velocity assumption. We will take a look at the closed form expression of the covariance matrix for the one-step prediction. T is tk plus 1 is k plus 1 t over 2. So we have k times at which we made observation with a reference time in the middle of that batch of k points, spaced t units of time apart, and we predict one cap t units of time ahead outside the batch. The time for that is k plus 1 t over 2. So that's the t sub k plus 1. The covariance of my predicted position velocity vector for that point based on k observations, which is denoted as pk plus 1 given k at point k plus 1, which I don't have yet based on the k points, based on the same equation, the same kind of equation as on the previous page. What we have is expressions in terms of k, and they don't tell us much until we evaluate and look at this. And that's what we'll do next. We'll divide by sigma square. So really P11 over sigma square. If I have 2 points and I predict the third point, the variance is pretty large, is 5 times larger than sigma square. If I have 3 points and I predict to the fourth, is only 2.33, and after 6 points the accuracy of my prediction is finally better than the single measurement noise variance. So you need several points for prediction, and this is a one step ahead prediction. And you can do a similar analysis for the velocity that goes down faster. I divide by sigma square but then multiply by t squared, so I end up with a dimensionless quantity here. Now, this shows the 1 sigma region corresponding to the one-step position prediction based on 2 observations. In practical situations, when you use remote sensing and you get 2 points from 2 measurements from an object, what you would like to know which way to point your sensor to come up with a third observation. So from 2 measurements, you look in the space, in the measurement space, in the region that gives you a straight line extrapolation, but now you don't know where that measurement will be because you don't have a perfect prediction. Therefore, you have to look in a larger region.